All right, looks like we have like a smaller group, but that's perfectly fine, and so we can have probably more discussions, interactions than having a bigger group. So so first, some introduction of myself. My name is Chi, working with GHD. I'm an air quality technical director of the mid-continental air quality team, and we do all the air dispersion modeling, permitting, compliance work for the mid-continental US. But also, on dispersion modeling, we also work pretty much for the entire US. So so today, thanks everybody to come to this session, and we're going to talk about air dispersion modeling basics for permitting. Actually, I was thinking to do this training course like starting from last year. Didn't get a chance to put together a lot of things, but eventually I get this thing put together. So I'm happy to share with everybody. So in this training course, we are going to talk about very quickly talk about dispersion modeling, what and why, and have a very overview of the air modeling system. And then we'll talk about how to set up a model run, like puzzle everything up. What information you need, what data you use it for modeling, and we'll at last we'll cover some regulatory modeling procedure. So to begin with, I understand there are like 3 main, graphical user interface on the market, but we are not endorse, any one of them. Any one of them is good. I have used all 3 of them, in my career, and I would say, not much difference, among the 3. If you, get with one, you get used to it, that'll be a great one for you. And other than the graphical user interface, for doing this air dispersion modeling, you can, if you know how to do the, input file in the text file, and you can download the EPA's kind of air model executable, and it's free. The best thing, don't have to pay anything. The user interface is the commercial version are not cheap, but they charge a reason. I think it's a reasonable amount of money, but for the EPA version, it's readily available on EPA's website, free for charge, and you can do modeling everything. So first things first, what is dispersion modeling? So it's actually a mathematical model to predict or simulate, the pollutant concentration as a result of, one or more emission sources, considering, the following factors like emission source characterization, and the surrounding environment, distance and time by the emitted pollutants, how it goes from the source to the ambient air. And of course, there will be consideration of meteorological and terrain effects. And we have various types of air dispersion models. We have Gaussian dispersion model, use Gaussian dispersion equation, and it's a steady state situation. It basically means, the concentration of the modeled pollutant over a single direction are calculated at every selected distance. Like, you just like a torch. You like a flashlight, open the light, means it, kind of basically start to emit, and all the trajectory, the light, you see the light, basically it calculates. It basically immediately move, the emissions to, whatever far away. So that's kind of steady state. And we also have a dynamic simulation Lagrangian, puff model. We'll usually do the CalPuff. By the way, I forgot to mention the air dispersion model, the Gaussian, the air model, air screen 3 are all Gaussian models. So the Lagrangian model, they actually model like simulate a puff of air starting from the origin. So it can actually, go, time step. Every time step, travel and disperse at a direction, at a speed. So it's like a more complex than the Gaussian. The Gaussian, this hour in this direction, the next hour to the other direction, and the 2 different hours, they don't communicate each other. But the puff model, the puff goes, every puff is dependent on the previous puff. And also the last, we have Eulerian, box system, Eulerian model. It's basically, you kind of like have a grid of cells. Pollutants are like emitting one kind of like cell, and it disperses to the nearby cells, and that is more complicated models like a CMAQ or CMAX. They kind of like we use them for ozone transportation reaction model. And this presentation, we are going to focus on Gaussian model and basically the air model that we use it most at regulatory world today. So why do we use dispersion modeling? Like this kind of like my air pollution control course 101. We predict air quality impacts for future sources. That's people will ask why do we not monitor it? One is you cannot monitor for future emissions, but you can model it. 2 is cost. Instead of monitoring the site, it's way more costly than just run a model. And you can isolate and identify source contribution from a large group of emission source. You can try to identify, okay, so this is the culpable source, while the other sources are fine. But from monitoring, you won't be able to tell that. And the force is the results are reproducible. As long as your input is the same, your model is the same, every time you run it, it'll get you the same number of answer. But monitoring is different. You probably will never have 2 exactly identical, monitor reading at 2 different times. So that was the air mod, kind of like why and what, but dispersion modeling. So next we talk about the overview of air mod modeling system. So this is like a sketch. So the air mod system, starts with some surface characteristic. There is a program called air surface, like it'll evaluate the surface condition and tell you get the data from all the database to grab the albedo, Bowen ratio, and the surface roughness for use in the meteorological process. Meteorological process, on the other hand, takes the surface observation of the wind direction, wind speed, and all the different kind of like solar radiation kind of thing from surface. And there is an upper air like profile, profile building file called upper air file. So you will take some surface characteristics, put in the air mat, and supply with air minute. Basically, there are some 1 minute data to supply to some air met, kind of like hourly met data that's missing. So once you get that, you will have 2 model ready metadata file, and that you will be used in the air mod. Air mod talks about the emissions and their dispersion, and at the same time, you also have some building downwash effects, like the building down the BPIP prime. That program will tell you, how the building is affecting the plume. And of course, the terrain, you will get the data from national elevation data sets to, assign an elevation of your source, your buildings, your receptors. And that effect is taken care of by air map, and air mod will then take all the, base, thing and put together in the model run. So we just did an overview. So so after that will be the key part of today's training. Divided into two parts. One is to set up an air mod run. First we will talk about how to set up an air mod run without knowing, without dealing with any kind of like the required regulatory, requirements, how to set up air mod, kind of like to meet the regulatory requirements. That's the second part. The first part is basically go through the air mod setup flow. So there is a total of 5 key input pathways into the air mod model. So their control pathway, the source pathway, receptor pathway, meteorological pathway, and output. But basically, control is basically tell the model what you are running, like what kind of pollutant, what averaging periods, what kind of options you use. Source pathway, very simple, like, you will know that it's basically to characterize the source, where is the source, what's the source parameters, what's the emission rate from the source. And of course, it'll contain, what kind of like a source group you want, what kind of, building downwash effect you'll have. That's all in the source pathway. Receptor pathway is usually the longest part of a air mod input file, like, the run file, because it has a very long list of receptor, but, its content is actually most straightforward. It's basically X and Y and Z. And, there are some, flag height, flagpole height, for the receptor, where is it? Do you want your receptor on the ground, or you want your receptor elevated? It's pretty much like a, list of locations. And the meteorological pathway basically tells the model where to look for the metadata. And, of course, you can give some information of the metadata in that, in that pathway. Output is basically tells the model what kind of output you're looking for. You're looking for 1 hour average, highest first high, highest second high. And do you want a contour plot? Do you want a frequency analysis? Do you want to do any a contribution analysis, things like that? So first, we're going to talk about the control pathway. So the control pathway we just discussed, you will give a name to the model, and what kind of model option you would be used. And what averaging period to be used, or what pollutants, or will urban or rural dispersion, or we will discuss that in more detail in the next slides. And that is a screenshot, basically part of the model input files. I mean, I will have those kind of like a sample, model input file, kind of like a extract throughout. Pretty much like 5 different places where every control pathway I have like a screenshot of that. Don't be scared away from those. I mean, these information will just be checkboxes on your third party or commercial user interface. So they'll give you like a box to enter your title of the run, and and model options will be just a checkbox whether I want to default or not default, and what kind of thing, or an averaging time, pollutant ID, and run or not run. I mean, run or not run is not very commonly seen in the user interface, but because they will basically tell you, okay, run the model, like click the button, or I don't want to run the model, but I want to verify if my input file is valid. They have a verify run. You can click that and go through the process and tell you whether model input file has any warnings or or fatal errors. That's basically, you can do that in the model info file by calling it not in the, run or not here. So, so we just talk about options. So some key options, most important, I'm talking about some most important options that we will use in dispersion model. The first one is NOx to NO2. So we know that when we are doing emission calculations, we usually calculate NOx emissions. We have emission factors or like quad I, quad J, they will give you like basically NOx emissions. NOx is composed of like basically NO and NO2. However, the National Ambient Air Quality Standard is not regulating NOx, it's regulating NO2. So we need to convert the NOx that you calculated emission to NO2. There are 3 tiers of doing it. First tier, of course, the most conservative. It assumes all the NOx converted to NO2. You can definitely do that. And it's going to give you very overly conservative results. Tier 2 is where we use most of the time. It uses an ambient ratio method, kind of like assume a ratio in the ambient air where like a NO, NO2, and NO NOx have like a ratio between them, like, but it's not in stack, it's already in the ambient air. So I don't know if you guys had done modeling before. A few years ago, we don't have this ARM2. We have the old ARM, the ambient ratio method, which is now obsolete. The old ambient method assumes 80% of NOx converted to NO2 for short-term evaluation, like 1 hour NO2. And it assumes 75%, NOx converted to NO2 for longer annual period of evaluations. That is like a very rough estimate, and the EPA find it not accurate enough. And of course, there are people thinking, okay, so maybe 80% or 75% is still overly conservative, not to their benefit. Many of the time they will go to tier 3, which is a lot of effort doing the analyses. So EPA came up with a new like a curve fitting approach for ARM2. So basically, they use a 6-order polynomial regression equation to convert predicted NOx to NO2, and we can see here. Sorry. So this is very small. At different NOx ppb, you have 100, 200, 300, and your NO2 to NOx ambient ratio is coming, from all the way to 1, drop down to somewhere like 0.2. So it depends on what your model has, predicted for the entire kind of like in the atmosphere that in your model, it'll decide which the ratio will be. So you can see in some cases there is like only 20% of the NOx converted to NO2. However, EPA, there are some people, complain about that. In some cases, the 0.2, 0.1 is really underestimate NO2. So now the EPA come to put like a minimum conversion rate of 0.5 in the model. So if you don't select your own ratio, AirMod will assume a minimum of 0.5. It will not go further down. So that's basically the ARM2. And the suggestion is to, if you just started doing modeling, you always select ARM2. Don't select any other option. Don't do tier 1. Tier 1 is too conservative. Tier 3, like ozone limiting methods, all need to have that ozone or very different, kind of like a more complex, kind of like a setup, which which is a great tool, I can tell you. And I'm not going to cover all the different. Every single method can be a 45 minutes presentation. So the next option we often think about is whether this is going to be a rural or urban dispersion coefficients. So there are two methods of deciding whether your study area is urban or rural. So you draw a 3 kilometer radius circle around the model site and look at the land use type. If they are heavy industrial, light models for industrial, commercial, or residential, and more than 50 accounts for more than 50% of your 3 kilometer radius circle, then it's a urban area. Another way of doing that is same 3 kilometer radius. You go look for the census data, see the population density. If it's greater than 750 people per square kilometer, then you can use urban dispersion coefficients. And I work with I work with TCEQ very often. Sometimes they suggest they suggest actually using a 10-mile radius to have a larger analysis. And what to put in the urban area population, and when you say this area is an urban area, or urban area, actually you actually get some benefits on the dispersion. Because urban area you have some heat island effect. So that sometimes with dispersion. So if you choose rural, that's always conservative, safe, and no need to justify. If you choose urban, you need to supply these information to the reviewing agency so that they can review and approve that. An urban area population, what you put in there? Like I always have a question because there is not very clear instructions, anywhere. So we did some research on the user guide and some, help file on the user interface software. Basically, we usually use the metropolitan statistical area for that area. Like, if you are having a site in Houston, you just put in the population of Houston, not the greater Houston area. That's the consolidated MSA that counts in Houston, Sugar Land, Woodlands. No. You just look at the Houston area, about like 2 million people putting there. And another conservative way of doing that, sometimes I'm still not very, confident of putting that a big number into a model. I just use that 10-mile radius, how many people are there in that study area. And it's not going to change a lot to your model file because the urban algorithm only dependent on the population to the, one quarter power, therefore not very sensitive. Okay, then the next slide here, we talk about some options that we use. It's useful, but it's non-default. You cannot submit that, but that'll help you to go through your, scenario analyses, sensitivity analysis, kind of if you want some results real quick. Is that something you can think about? First, it's like a flat. Just assume flat. There is no hilly situation. So and you can run skip air map. That's a lengthy process sometimes. And you can run assuming everything is 0. It doesn't have to be 0. If everything is 100, everything is 0. Your result is going to be the same. It's just like you move it up. Of course, you at the same time you moved your metadata also up and down. But really, to my experience, I don't feel running air maps is very cumbersome. So I don't usually use that, but this is some option you can use. Think about that. I mean, and this is only suitable at those flat areas like Houston, Galveston, probably okay, but probably not a good idea if you do something Austin here. And faster running options. Area source, area source, air mod actually use a numerical integration, method. So it'll optimize that, process. They're calling it optimize, they basically cut some calculation or make the model run faster. Faster all, same thing, that is for area source, that's for point and volume source. And if you do have area source, when you select a fast all, it actually, activate all the fast algorithm for all the sources. And if I only use it for, doing, if I do need to get the results real quick, with the computing power advancement, I have like a computer with 80 processing cores. I don't necessarily use the fast, but it's neat. It's good functions there that you can use. So we talked about source, how to control. The next is we have source pathways. The source pathways in the air mod. Kind of like the input file look like this, but in your commercial user interface, it's probably pretty nice that you have a tab asking you, okay, so this is one stack. What's the stack parameters, emissions, all that information? Just you enter the data instead of writing that thing. But you can write that thing if you are getting used to it. So in the source pathway, we basically give coordinates and elevation, the location. What type of the source? I'm going to talk about point, volume, area, but there are more other sources types available in the air mod, but it's less frequently used. So skip that today. Downwash parameters, also included that in there, and we can also use operating schedules. We can also do source grouping. So now let's talk about some source setup. Point source. Point source is your stacks, vents, exhausts. Those are like, they're very clear. It's organized, release. The source parameters include emission rate, height, temperature, velocity, diameter, and I find it like, of course, first is emission rate, and I remember all the 4 parameters is HTVD, but I changed the sequence and put the diameter up. The HDTV sounds like a pretty nice flat, screen TV at your home. So that's how I remember it. But now that we have even better 4K TV, 8K TV, and HD TV is no longer anything good. So, but there's something you can, I use to remember that. And there are like some special point source like pseudo points, flares, cap stack, horizontal stack. And we'll talk about that, in the next slides. So stack height. Stack height, you just put in the physical stack height of the stack height. Do not include plume rise. We know that, in this, like there are some plume rise, and you will have a question, should I put in this height or this height? And, air mod actually takes care of these. So you just need to put in this height. And also another question, some people always ask me, do the stack height, does it come from ground or come from the roof? And if I have a building and I put a stack on top of the building, like it's in the building, like in 2D view, you put a stack on the roof of the building. So which height do you enter? Anyone knows? Ground or roof? Yes. And in fact, air mod, it's not smart enough to figure out here is a building. Even though you put a building in there, it shows on your user interface, a graphical interface, it's a building, but air mod doesn't know it. Air mod only know the stack from the ground. All right. Do not use stack height taller than the good engineering practice height. what is that like, if you have a very tall stack, you probably, because, you want a good dispersion parameter, and, you have buildings around it will cause some, building downwash. But the good engineering practice height basically is at a level that your stack no longer is affected by building downwash. But there are stacks built higher than that. So the GEP height is actually either 65 meters or, determined by, you have a building downwash model on BPIP will tell you if, that GEP height is higher than 65 or not. If it's not, if the building downwash program determined the GEP is less than 65, you can still use 65 as a GEP. So your stack, you still can build your stack to 65 meters. This only applies to like very large plants. I mean, 65 meters, think about it, 220 something feet, super tall. So, but if you build even taller, and your model tells you you don't have to build that tall to avoid building downwash, you cannot enter a stack height higher than 65 in the model. Temperature. Temperature is pretty straightforward. What is temperature outside, going out, exit temperature out to the atmosphere. But there are some special treatment. If you don't know the temperature and just want to use the ambient temperature, that can be get from a metadata, just put 0. Doesn't mean absolutely 0, otherwise nothing is going to come out. Negative, you can also put a negative number, but of course there is no negative temperature at all, like, scientifically is 0. But so that actually means use the ambient temperature and add this, like minus 10, add 10 degree Kelvin. So it's actually 10 degree, not F, for sure it's not F. So it's but the delta, we're talking about delta, Celsius and Kelvin are the same, right? So you will be basically adding 20 degrees to the ambient air. The air mod can take that. Very seldomly used. Most commonly used is 0. Like sometimes you don't know or you just know that is like basically ambient air, ambient temperature. Just use 0. I have not used that before. Velocity, is another velocity, diameter, flow rate. We usually get flow rate, and we get diameter, from our, operators. Nobody talks about velocity in operating, but model for some reason it calculates velocity. So every time I ask a client, hey, what is the velocity of the stack, they'll just look at me. What are you talking about? But they usually give you ACFM or DCFM or what, like a kind of like an actual cubic feet minute. Basically, as modelers, this is our common exercise to convert like cubic foot per minute to meters per second based on the diameter. And I have been, some of my team members sometimes get confused. I tell them this is a triangle. In each corner is a 3 factor. You have 2, you can have the other one. So now let's talk about pseudo point parameter. Like, what is pseudo point? Pseudo point is something that you want to model as a point, but it's either not a point source, or it's you don't have complete stack parameters. So the parameters so air model, like a guidance, you can actually put in a source acting like a point source. They're not acting, just like you enter the parameter as if it's a point source, and you can use like the model will take it, will give you some model run results based on these things. So the default, we call default, like when you are missing stack parameter, you use the default parameters. The stack height, you would use, I would use the actual release height. That's Texas guidance. Louisiana guidance, just use 1 meter. I mean, if you do have the actual release height, you're not missing it. So you don't have to use 1 meter unless you don't have a release height. Then you can use Louisiana's guidance 1 meters. Temperature, assume ambient. Velocity is like 0.001 meters per second. That's kind of 1 millimeter per second. It's kind of like not really moving at all. That basically suppress the upward momentum. We're not giving the pseudo point any upward momentum. Diameter, if you don't have diameter, use 1 millimeter Texas guidance, use 1 meter Louisiana guidance, and other states, they probably have their different guidance, but one or the other is very common. And also, if you have a capped or horizontal stack, we used to use this, but now in air mod they have their own stack type in air mod, so you don't have to set up pseudo point. Just tell air model this is a capped or horizontal stack. So pseudo point source, I would always use it as last resort when you don't have any information. Because some equipment fugitives or tank lengths, I would usually rather model as volume source than pseudo point, and always try to get real parameters from vendor specification. Otherwise, you're using default, you can run it, but your results won't be good. In another presentation I did yesterday, I kind of like showcased how I asked ChatGPT for a RTO stack parameters. If I don't have it from my client, ChatGPT will just pull some information and I just put it in the model. And after a couple of weeks, the client will come back with me with the true, parameters, and the ChatGPT got it pretty close. So that's the suggestion. Although I have a slide, I strongly discourage you to use that. And flare. Flare is another, type of point source we use. I mean, there is no flare source type in air mod. Air mod does not model a flare. Air mod actually use the point source setup to model the flare. The velocity is locked at 20 meters per second, no matter what, how much, flow you are sending to the flare. Temperature always 1,273 K, which is 1,000 C, which is 1832 F. But, in the model, you usually just put in the K. And effective height, there is a effective height calculation. Texas is easier, just to put in the, flare height. EPA, kind of like a method, you have a different way of calculating it. Effective diameter, they both calculated on the gross heat release input, but Texas will take into the molecular weight as well. So that's kind of like the flare. Point source and some other dispersion techniques. So we talked about before, you don't want to put in, more than 65 or the GEP height, because that's not allowed. And other dispersion technique, you cannot just, do something to, you are not supposed to do something physically just to help with dispersion. So if you have a stack, you have a, flow rate, and you modeled it and find it's not passing the model, and you think, okay, if I have a higher velocity or flow rate, it can get better dispersion. So you just add a fan to it. It's not, physically you can do it, have higher, flow rate, but, it's not allowed for, modeling analysis. That's kind of very tricky. If you do that, make sure you have good, documentation, support why you do that, other than dispersion purposes. Maybe you need that to, kind of create a negative pressure, or you need to do some pressure thing, the safety, and that's okay. As long as it's not solely for dispersion purposes. All right, the volume source. Volume source is something like this, like equipment leak, fugitives, We use volume source. We also use like loading activity that they don't have like a stack to organize everything to be emitted from like a vent or exhaust, like it's spread it everywhere. That's kind of like we use volume source. And source parameter will take a emission rate, also release height. There's initial lateral dimension, like initially how big the volume is, but there are some calculations. It's not just simply the size of your area. And some calculation, I'll have it on the next page. And some other types of volume source I have it on the next page and the following pages. Okay, so this is how we calculated the parameters. So think about this is like a block of this area. You have a lot of flanges, valves, pumps. You're modeling its fugitive emissions. Look from top. This is y, x and y, and from the side, you have this at the ground, and you have a height c. So air mod assumes all volumes are perfect squares. It doesn't really kind of like take x and y. So we'll calculate a equivalent side of the length. Basically, ask the question: what's the equivalent side of this rectangle if it is a square? So basically, x and y take your square root. However, aspect ratio should not exceed 2. Like it shouldn't be a very elongated, volume source, because that way it'll mess up with the model, kind of like, it's basically you are bringing all the emissions from 2 ends to the center and make it much bigger instead of a long building. So if the aspect ratio is 2, we recommend to represent with multiple adjacent volume source, and that's the side that's the side, and the height, release height, or vertical span is basically, if it's ground based, and vertical span from top to the ground, and the release height we usually take the center. This is extract from the modeling guidance on how you will calculate it. There are different types of volume source. There are ground-based, there are elevated. Elevated, there is also on adjacent to a building or not on adjacent to a building. You have, your initial kind of like dispersion, initial lateral or horizontal parameters calculated using these equations. And I wouldn't be too sweaty about kind of remembering the numbers, because if you use a third party like a graphical user interface software, you just need to tell it x and y and z. It'll probably calculate everything for you. And if you don't have commercial software, you want to do the calculation, just TCEQ's email workbook. The TCEQ is basically a modeling workbook. Can also calculate that for you as well. And to talk about adjacent or like adjacent or separate volume source, this is a graph of like if you have an elongated building, and it can also be an L shape or whatever shape. These are the volume source setup. And this is called adjacent. These are not adjacent. You put a volume source here, a volume source here. This is a gap. This was an idea that was developed in the early days where computing power was not strong enough. So they tried to calculate less and to have faster calculation results. But now with better computing power, we never worry about this. So this is very seldomly used. We usually use this like adjacent. So every part, you don't have a gap. It's more accurate representation. So what kind of volume source we were talking about? Like like storage tanks. So there are different like internal fixed roof, external storage tanks. We said we can use it as volume source, modeling volumes. I used to model them as pseudo point, and it gave me really bad results So I consulted with the state agency and modeling team, and they suggest me to use volume source. So the internal floaters, they have vents. They have vents all around the top roof. So the, they actually, you can treat it as, this is initial kind of like a dispersion already. So it's, so the side of the length of the side you can take as, the tank diameter will be your X or Y, and basically you put it in there. And elevated, it is treated as an elevated source, but it's on or adjacent to a building, which is the tank. And the release height will be at the top where the vents are, coming out. And sigma Z, which is the initial vertical kind of like, it's going to be based on the tank body. Fixed roof tanks, very similar to internal floaters, but the difference is it doesn't have vents all around. It has only a gooseneck vent on the top, probably sometimes in the center, somewhere. That's like one, maybe there are two or three, but we usually model it one. So the initial, the length of the side of volume source is not going to take the whole tank, but take the opening of that vent. It's a pretty small vent, so I usually just do 0.1 meter times 0.1 meter, something like this. Usually it's good enough. But release height and initial vertical dispersion will be the same as the way that we doing with internal floating roof. External floating roof, we usually treat it as like open top tank, because we usually use an area source. That's going to be talked about later. So that's all the volume source. So area source, another type of very commonly used source in air mod. Usually like those open top tanks, like the wastewater tanks, like a wide opening an area, or those ponds and lagoons, those can be modeled. If they have any emissions, they can be modeled area source. Area source, I haven't touched that, or the point source, volume source. The emission rate is taking, the model is taking gram per second. Basically, it's mass per time and pound per hour, right? You have pound per hour number, you convert it to gram per second, you give it to the model. But for area source, it's different. It's actually doing a numerical integration. It's basically calculating each one piece by piece by piece by piece, and then like make an integration, and like they actually do like a sum of your impact. So it's basically you give the model gram per second per square meter. It's kind of like your emission rate. Still, this is the whole emission rate per area. So that's the number you give it to the model. And you can actually give it an initial vertical dimension as well, but it's an option. Usually model will take it 0 if you don't give it. Okay, now we talked about all the setup for the sources type, different sources types. We talked about point, we talked about volume, we talked about area. Now we talk about some other things that we can give it to the source group, source pathway. The source group, you can group, a bunch of source in a group and give it to the model and let it actually to evaluate their impact. A source group can contain one or more sources. So then you would ask, why do we do one source in a group? Because if you don't do that, air model will give you a overall impact in a default group called all. And that all group has, basically added up all the impact from all different sources. So you won't be able to kind of look at every individual source, what their impact is. So that is, we usually use that single source group to evaluate the impact, kind of like for the specific source of interest. And one thing to note, when you set up every single source as a group, and you want to look at it, you will have all the results, and you have each individual source results, and you try to add them up. You find that it's not, consistent with all, results. Why is that? Because each and every single source that impact is at a different time and location. But, in overall, they actually pick the, worst case, for all the overall impact, not like individually, worst case, individual worst case, time and location, they may not match. So it can, at the maximum, the worst case of the overall, that kind of like impact, it will not necessarily be the same worst case time and the location of any single, source. So that's kind of like the nice thing we call refined, model around that, kind of like, can help you to, arrange things apart so that your overall results is more accurate. You can also, in the source pathway, you can also do some, variable emissions. So you can vary by season, like you can say in the summer, I'm operating less, while winter I operate more, and I have more emissions. We can do that. And can be by month, can be hour of day, can be day of week. These all can be given to the model. The model will be able to address that for you. However, the date I would mention is the day of week. That should only be used in long-term models and shouldn't, such as annual average, but shouldn't be using, short-term. But why is that? Because you would say my plant operates from Monday to Friday, and Saturday and Sundays everybody's off, and we have no production. In reality, this can be true. However, the short term, you're actually looking at the worst case 1 day of impact, the worst case 1 hour of impact. And the metadata you use is typically from past. It's not for this year. You don't have the metadata for right now to model, right? So if you use the previous years, like in the past, historical metadata, you cannot guarantee all the bad weather, is only occurring on, weekends. It's kind of like force majeure, you never know. Today you have a good weather day, it's a weekend, or it's a weekday. I'm happy because, because the operation never knows what operation don't know whether this is a good weather dispersed day to do it, and the good day not necessarily only happen in weekdays, and it could be a bad day that in a weekend that you missed it. So we cannot use that for short term. And we can also combine the above variation. You can do hour of day plus months, plus season. Like you have 4 seasons. Every season have different hour of day emission. Hour of day that like you will say, I operate my facility 7 to 7, or 9 to 5, or 8 to 6, something like that. That can be done, and that actually can be a permit condition in your permit, that you'll be limited to only operate during the time that you said you model for. And then you can also do by wind speed, and also actually, for further step, you don't even have like a season or month distribution. You can also have an hourly rate file. Like every single hour, you can feed air model a emission rate for each different source. Well, that's very complicated. A very complicated project will involve this. Receptor pathway. We are. Yeah, I think I will hit. We started at 1, so we have. So I want to stop here. I would like to open for some questions about source, controls, anything else, setup, and you guys have any questions when you are setting up a model, or, what else, like information you are looking for, or something I went too fast? Any questions?
So did you say all the commercial dispersion modeling products use AirMod as their base?
Yes.
User interface? Okay.
Yes, there are, they basically use AirMod as their core. You basically have a, graphical, kind of like interface that you can draw a stack, draw your property boundary, and, basically it'll have very complicated, not complicated, well-developed way of creating your receptor grids, and all the things that you don't have to kind of like think about something like this. You don't know the sequence of number you put it in. Maybe gone too far.
Yeah, I was just curious about like dispersion coefficients and like the NAAQS conversion factor.
They are all built in there.
Yes, they're all, it's the same as we all.
Yes, yeah, it's all like the different, as long as they call, I am, building a graphical user interface for AirMod.
Yeah.
There are user interface built for CalPuff. Don't confuse about it.
Okay.
Yeah, so otherwise you will have a totally different model.
Yeah.
But AirMod is AirMod.
And so from like a permitting perspective, do
Yes.
they only use the AirMod derivative? Will they only accept the AirMod derivative
Yes.
softwares?
Yes. For usually for AirMod, like for regulatory permitting, you use AirMod, but there are some special cases. If you need to examine ozone, you probably need a different model. And if you do some other, like class 1 area, which, like talk about like a long range transportation, then you probably use CalPuff. And because AirMod, it has the Gaussian, the accuracy is up to 50 kilometers. Over that, it is no longer that, accurate, so we use other models. But, mostly the 99% of the air modeling project, we use AirMod.
Okay, and so there's like the Lagrangian and the Eulerian
Gaussian,
models, are those more
Gaussian.
for like academic research purposes?
Hmm?
Are those other models?
There are other models like Eulerian.
Yeah, so they're more
Eulerian
like
is,
research.
yeah, you use for research, and also use for the secondary formation of pollutants.
Okay,
It's very good because it takes into the chemical reactions,
gotcha.
and chemical reactions is the core, and the transportation is actually a kind of small part of those models.
Okay.
Yeah.
Thanks.
Any other questions? All right, I'll take that as a no, and we go to the next path, which is the receptor path. And I hope to, stop at about like 1:25-ish. So we'll have the coffee break and come back, and we'll continue to talk about, the regulatory process and other things. And I don't think I'm gonna take the whole 4 hours. I probably will, kind of like finish a little earlier, and for some questions or discussions, or, yeah. Receptor pathway. Receptor, like I said, is just X and Y and Z. And anyone can, like from just looking at the numbers, anyone can tell what the shape it is. The shape of the 4 receptor, or what, when you connect the 4, what does it look like? It's kind of like, so that's kind of like a benefit of using a graphical user interface. You don't have to worry about those kind of things, And, just like, I sometimes find it fun to like, to think about these things. And this is a perfect square. Like 0, 100, 100, 0, right? The 700, 700, 600, 600. It's a 100 meter square. So that's kind of like, what you're going to see in the, in your, receptor grid, that pathway. And in the reality, this list is never going to be only 4 receptors. It's going to be a list of at least 4,000. So, but there's no requirement at all to look at the numbers and reflect in your brain how it is look like and where it is. But so this is kind of like the receptors that we feed into the air mod. But there are different type of receptor grid. You can put in Cartesian, you can put in polar, you can put in discrete. And this is the thing that I show is discrete. Like you basically in the user interface, you can actually put like single as you want, but usually you don't do that. You just follow state agencies kind of like a general guidance on how to build your receptor. Because of that, we usually use Cartesian and discrete. We very seldomly use polar. Polar is more like like a round circle, and your first level is more kind of like a tight. Next level a little loose and even looser. And we in the regulatory world we almost never use that. Most common approach, we create a multi-tier receptor grid, and then create a boundary receptor grid and remove all the receptors in it. Okay, so you don't have to put receptors on your own property. And then sometimes you have to remove duplicates. But if you don't remove it, that's also okay. Like, just to have the air mod just run one more receptor. It takes a little longer, but not end of the world. And sometimes you convert everything into discrete receptors, easy to manipulate. So the receptor parameters are pretty straightforward. X and Y. Elevation is Z, hail height, and the flagpole. Okay. So the guidelines, what to, this is the guideline of what to do with receptor setup. Like these are all the regulatory guidelines. So the boundary, you basically pick all your corners of the site and connect them and place intermediate points on there. They could be 25 meters apart, they could be 100 meters apart. That's kind of like up to your state agency's requirement. And you put a different kind of like levels outside your boundary, like a tight grid, each is 25 meters apart, and fine grid, the medium grid, coarse grid, like the more farther away you go, the looser you put. And where did the grid start? That's kind of like a question, like, I used to get confused. Louisiana said, extend from the property boundary to 1 kilometer. But of what? Didn't say. Is that from the source or from the boundary? And from the source, count 1 kilometer, or for the boundary, count 1 kilometer. Not clear, but Texas makes it a little more clear. It should end up to a certain meters from the source being evaluated. So that basically being said, this is, if there is only one source, this is the receptor grid you would kind of like make. This is your facility boundary, and your source is here. You count 1 kilometer. This is your fine grid. You count 5 kilometers. This is a medium grid. Of course, you count 10 kilometers, 50 kilometers. That's your coarse grid. That's kind of, you only have one source. What if you have more? You can follow the TCEQ guidance, but every single receptor you want to count 1, extend it to the limit. We'll count 1 to the limit, count 1 to the limit, count 1 to the limit, right? And the same thing, you do it for 5K kilometers. So it will look like like very similar, rectangle at the inner layer, but it will, this will become less important, and the outer level of your receptor grid will more look like a square. And it doesn't matter, this is the previous slide, it doesn't matter that on this side you don't have a fine grid. The fine grid can, stop here, and this is all in the facility. You don't have to put the receptor. Your receptor will be looking like a square that, this is not, and on this side you don't have, you start with medium grid. That's fine. But you don't want to like do all the kind of like the thinking, to make these counting, there is like a easier way of doing that. It's basically extending it from property. You definitely will have a more than enough, receptor grid than the state requirement. The pros are easy to set up. Cons are apparently you are including some additional receptor you're not required. Not a big deal. Just runs a little slower. So if you are looking at quicker run, that's something you can optimize. So other discussions. I would use round numbers for the fine, medium, like for those kind of for this, you probably where it is your physically on like you probably do it on Google Earth or like on the survey map. It is what it is. It'll have like a very unrounded number, like 1, 2, 3, 4, 5, 6.78. But that's what I found. For the fine grids, like these kind of like Cartesian grids, where they are 25 meters apart, 100 meters apart, 500 meters apart, I recommend to use round numbers like that. End up with 0.00, and 2 benefits. 3 benefits. When you look at the list, if you don't have if you're working with like a text file, you don't work with a user interface, you can distinguish with those Cartesian and your boundary very easily. Your boundary will be something 34.56 meters, but your grid will always be 100 meters even, 200 meters even. It's very clear to find out. And by looking at your results, you suddenly know, oh, this maximum impact happens on my fence line boundary, or this one doesn't happen on my fence line. And of course, it looks neat, and regulators sometimes will ask, why do you put your grid on a non-rounded file, kind of like on a non-rounded numbers? Sometimes they'll suspect, are you trying to move like maybe within the 100 by 100, they're the highest spot maybe in the middle, and you didn't catch it. But if you are doing the round numbers, they will not have that question. Metadata. The metadata, the metadata, the air mod actually takes 2 pre-processed metadata file for each run. It's a surface data and upper air data. We talked about that before, right? So, and another important input to air mod run files is the elevation of surface observation station. So this one is actually, I'll discuss that in a later slide as well. And this metadata is basically processed. Raw metadata can processed by AirMat, and that is not covered in this presentation. But this is how the metadata block look like in the model. Basically, you tell that where the surface file is, where the profile, the upper air file. The profile is basically the upper air file, and your data, if this is the site number and the starting year, and basically the model will, you can take like where the airport it is, like where the monitor station it is, upper air data, and this is the prof base, like the profile base, and where the base level is at. So where to obtain those data? So it's important, you know where to obtain those data to do your modeling, so that you have all the information ready. All right, so you can process raw net data. You can download all the observation data from lots of sources. You can process them and do your own metadata. But as a regulatory model, I mean, few people really do that. You can either process by air quality regulatory agencies like TCEQ. TCEQ provides the metadata for every county. And you can just download them and use them. You don't have to worry about it. And if there is anything wrong, it's on them. And you can try to find metadata from old projects. If the state doesn't have metadata, I think Louisiana doesn't provide any metadata for modeling. But Louisiana doesn't require a lot of modeling for any project. Texas does. Any small major project, modeling is needed. But also you can purchase AirMod ready metadata. This can be purchased from a lot of places. Other, the user interface, providers, from other consultants, and anyone who knows how to process metadata, you can purchase from them. So the metadata, I'm talking about something on the Texas procedure. So the TCEQ pre-process at least one set of metadata for each county. And each set of the metadata comes with 3 different surface roughness. So you will go to see a county. You will find 6 files. You will remember we have 2 files for a model, like a surface and an upper air. So it has 3 sets with low surface roughness, medium surface roughness, and higher surface roughness. Which one do we choose? Easiest one, just guess. And mostly you have medium, surface roughness. And that's a lot of times you can do that. And but now TCEQ has a question asked: how did you determine high or medium or low? And you need to run air surface. That's a program that remember the surface. That the sketch. The run air surface to find out whether the surface roughness is in between 0.1 0.7 or less than 0.1 or greater than 0.7. And then you run it, and then you determine which one to use. To my experience, I had about 2 or 3 projects. I turned out to be low surface roughness. And most other projects are medium. I have never seen a high. And there is the metadata. There is another question we left from the previous slide. The profile-based elevation. What is that? It's confusing. The name called profile-based elevation because upper air data is basically called profile data. But this profile-based elevation actually talks about where your profile starts. So it's actually asking for where your surface observation is at. And this number, luckily, can be found on TCEQ's metadata documentation. They will give you that number for every single county that is processed. Okay, so if there are 2 sets of metadata available for a county, which one should I choose? So an example is I had a project in the ship channel. So in the Harris County, there are TCEQ processed 2 sets of data. One based off the Hobby Airport, the other one based off of the Intercontinental Bush Airport. So gut feeling, right? Kind of like which one do I choose? I would choose the one closer. But TCEQ, when I submitted the model, TCEQ asked me, why do you choose the Hobby Airport? So that's kind of thing. Apparently, I answered. I just choose it based on because this is closer to where my project is. So this makes me think. I mean, maybe in the future I will add in my documentation and tell them why did I choose it. Just a 1 sentence, so that they can have 1 less question. If there are 2 or more counties, now there are 2 or more counties, TCEQ they process their data with same airports. Like, for example, in lots of the counties in West Texas, TCEQ will basically use the Amarillo, surface air, and they probably use a local surface but they use the upper air from either Amarillo or from another place, maybe a little south. But if two counties, I did a project in this county. I used these two, upper air and surface data. And tomorrow I do another county just next to it. I looked at TCEQ's data. They use the same exactly, surface and upper air. Can I use them interchangeably? Better not. Because, remember the raw data. The raw data being processed in AirMet, it's also paired with some, paired with different kind of like surface characteristic that you'll get from the air surface run. The air surface run will tell you surface roughness, albedo, and Bowen ratio. These will be different from county to county. So if you have the data, don't just use a neighboring county. Okay, so what if my model results are not favorable with TCEQ's data, but I believe TCEQ process data not representative to my project site? Answer is do your own work. And and it's not mandatory to use TCEQ metadata. They process the metadata on a very conservative mindset. That they're putting lots of conservative parameters when processing it. The intent is to result in a kind of very conservative number. If you can pass with that, great. If you don't, for very large projects, sometimes we'll just process our own data, and as long as you provide sufficient document and your approach is sound, it is acceptable. Let's see. I probably can talk about 5 more minutes on this, how to play with air surface. And we'll probably can take a break. So air surface, basically, in order to determine whether you're high, low, medium, or if you want to, process metadata, you need this air surface. You first download air surface and basically evaluate land characteristics. So your base information will be able to download from the MRLC, the multi-resolution land characteristic consortium. This is the website, and go and that picture was pretty old. Say NLCD 2016 is now available. Now you have 2019 data. So you download these 3 types of kind of like a surface characteristic for your model run: a land cover, a tree canopy, and impervious cover. Some note. Land cover data should be supplement. If you only have land cover data, that's probably fine. You just use that. You don't have to use tree canopy or impervious. This data should be supplemented with that concurrent. So if this data is 2016, you should use 2016 of tree canopy and impervious. You shouldn't use 2019 and the 2016 for these two. You'd rather not to use them. And another thing is 2019 data, you have this too, it's currently available. Land cover and impervious is available. Tree canopy is still not available on their website. So I sometimes choose to just use land cover and impervious. I just got a message from a comment from TCEQ, shouldn't use impervious without tree canopy. So you should just use the land cover. Some quick discussion on how to put your, do your air surface model. You need where your study area and location is. Put it on your project site. There are some cases you put it on the met station, but for projects, usually put on project site is more representative. Radius to use. Default radius is 1 million. And I did say sometimes you want a special consideration. If the site is very large, the site itself maybe it's more than a mile big, then I would sometimes think about using 3 kilometers. But I just got a comment from a project from TCEQ. They say, no, I'm still looking at 1 kilometer. Don't use 3 kilometers. I haven't discussed with him yet, there is some discussion we can have, but, we don't know. I mean, I'm not exactly sure on this because I used to think, you can, because this is allow, air surface allow you to, give a user input radius. Why do you have to lock it at 1 kilometers? Why the size is so big? Some, surface moisture, kind of like, also something to put into air surface, but, you can do either like I call this year of net data is like a dry or wet or average. It all based on precipitation. This one you can guess, like you can usually you can say this is average. That's not too bad. But if you want to be more accurate, you want to download the precipitation data from the past 30 days, not 30 days, 30 years. And if it's like first like top 30%, the bottom 30% wet and dry, in the middle is average. I mean that's a process, kind of like not too difficult. It'll also ask you about snow cover. Texas, Louisiana, don't worry about it. No snow cover, and no arid. I don't think there is any arid, locations in Texas, and frequency. Like how do you want your land use characteristic for TCEQ? When you're deciding where low, medium, high, just use just one sector. Don't slice it up. And frequency is same. Just use annual. Same, and don't slice it up to season or months. And airport flag, whether the site is an airport or not. Usually, if you put it on the project, it's not an airport. So that's now is a 2:25, and I'll stop here, and we'll talk about output pathway, and we'll talk about some additional setup, and then we'll go to the regulatory modeling setup. So, any questions about receptor setup and meteorological? Okay. No questions. I'll see you in about 45 to 50 minutes. Thank you.